another classroom, right? Okay, so let's just review directional derivative here. You got the homeworks due. Dang it. One move. Homework is due tonight at 7 p.m. for directional derivative. And I will post your written homework for next Thursday. That will be posted today sometime. So let's. So we're looking at this surface. This gold surface was a elliptical paraboloid. I'm only showing the part of the surface in the first quadrant or octant. I didn't say that last time, but of course this isn't all 8 octants. But I'm just showing you the part of it there in the first octant. So now I'm at this point on the surface, and I want the rate of change in this direction that I'm pointing here. Do this here. That's right. Okay, that didn't work at all. Maybe touchy. All right, so I want the rate of change. Gee whiz. I'll get it on one here. I'm showing a direction there with the blue and red vectors. Stop right there. That's what I want. Yeah. I'm showing a direction there with the blue and red vectors, and I want the rate of change of z of that surface in that direction. So you can think about that as, like, think about cutting a plane in that direction, like setting a plane in that direction, and then you want the rate of change, right? The rate of change along the trace that you get when those intersect. That plane intersects with the surface. So I want that rate of change. What is that rate of change? That should be an easy question. What's that?
Partial with respect to x.
Is it the partial with respect to x? That's what he's saying. Yeah, that's the partial with respect to x, right? We're going strictly in the x direction. We have that's a very special derivative, right? That's a very special derivative because it's only looking at x changing and seeing what the change in z is. That's the partial with respect to x. Likewise, if I point our vectors exactly in this direction, there we go. So straight, this should show straight up here, and then on that one, straight to the right. So those are showing the same thing, right? Positive y direction. So now the rate of change along that trace right there. So you take that trace, that rate of change is? It's the partial with respect to y. What could you predict about that partial with respect to y? Negative, right? If you increase y, z goes down. Okay, and then we said that we derived a way to get every rate of change for every direction that you could pick, right? So here's in the second quadrant, right? I'm pointing into the second quadrant, and based on the trace that we get, what would you predict about the rate of change in this direction? Positive, right? If you go in that direction, z goes up. You can see that on that, you're going uphill, right? And so this is some combination of what? X decreasing and y increasing at some proportion, right? And according to that proportion, then you get a certain rate of change in that direction. We did all the math last time for that. Okay, and then we said, let's turn the trace off. We said, well, we're interested in the maximum rate of change, right? So of all the rates of change we could get by going in different directions. Oh, and by the way, direction, when we talk about direction, that's a 2D phenomenon, right? That's just in the xy plane. And then the rate of change then brings in change in z, right? There's a change in z per horizontal change. So when you're talking about direction, you're talking about like R2 vectors. But then when you bring in rate of change, now you're talking about how z changes with respect to going in that direction. So that's just want to point that out. So now we said of all these different directions we could go, we're interested in the maximum rate of change. And what do we find about that? Maximum rate of change is in which direction? Yeah, so the gradient, so you have the gradient is the partial derivatives, they form a vector. And that vector would be in this direction in this case, and that would be my maximum rate of change. If I go in that direction, I'm heading up the fastest, and we said in the contour plot, that means getting to the next higher level curve as quickly as possible, which would mean going orthogonal to that line, right? And so that's showing this direction kind of somewhat towards the origin, not exactly towards the origin, but somewhat towards the origin gives me the maximum rate of change. So what about the maximum negative rate of change? Parallel to that and? Opposite direction, right? So if I go exactly in the opposite direction, I'm going to go downhill the fastest. So all I have to do is take the opposite of the gradient vector, and that gives me the direction. And then the magnitude of the greatest rate of change is the magnitude of the gradient. And then in this case, the opposite of the magnitude of the gradient. Which direction would I go downhill the fastest? Again, perpendicular to the contour lines. Okay, what about zero rate of change? Tangent to the contour lines, which is orthogonal to those directions of max and max negative rate of change, right? So going right along, walking right along the contour line. So there's two ways you can do that. You can go that way, or you can go that way. And what would that be? On your surface, that's like this. There it is. So going in this direction, so here's this level curve that I've made bold. I've made it bold on the surface too. And so it's like if you take a step, your z doesn't change, right? So it's rate of change of z of 0. So you have two directions that do that. Give a rate of change of z of 0. And what is that? Those are orthogonal to direction of greatest rate of change and least rate of change, and so orthogonal or parallel to your level curve. Okay, so then you'll practice doing just the computations, but all that stuff that I just talked through is really important that you're understanding that stuff, and then WebWork gives you some practice with computing those things based on all the math that we derived last time. Any questions on that? Okay, so now I want to, let's turn everything off here, except no, I want the point. Oh, I want that. Okay, that's good. Where's my other point? Okay, so let's have a different conversation here, but still, we've talked about it before. So this is my point. So this is my point in the xy plane. It's AB. And so then that would be in R2. And then, or you could say AB0 in R3. And then this is the point AB, F of AB. Okay, so I'm going to deviate out from that point. We've done this before. So this is an exercise for you. I'm going to deviate out from this point to some close by point, say xy. This can be any point nearby AB. I'm going to be close to AB. I'm just going to go out to a different point close to AB. Any point, anyone. Okay, there's no stipulation on that. The only stipulation is stay close to AB. Okay, and so that. What I want you to do is I want you to estimate, based on the math that we've been doing. So this is now the point x, y, z. And I want you to use the math that we've been doing to estimate that. So what is that? Find an estimate. And you're not going to actually find a value, but you're going to express it, right? So based on the stuff we've been doing in the last week, can you write an expression that would estimate that value of z that I get if I just deviated away from AB a little bit to the point xy, any point near AB? So can you do that? So see if you can think about that. Do it without looking at your notes. See how much you've learned.
Oh, okay. I mean, I'm pretty sure like those are correct, but the axes aren't making sense.
Okay, let's see how we did. Chrissy. We're going to ask Chrissy up here in front. So
Z would be derivative.
let's talk process, not just final answer, right? I don't know if you were going to do that or not. It sounded like maybe you were just going to tell me what it was. So
Okay.
what was your process of thinking about this?
So xy is given and it's near the point AB,
Right.
f of AB. So we can use the rate of change at that point.
Okay.
And then, so rate of change of x, it's like dz equals mdx.
Okay.
So that would be rate of change of x times x minus a. Because
Okay.
x minus a is the change of the x.
Gee whiz. I like that. Try at the bottom. So you're saying dz is dx?
mdx plus mdy.
Okay, so good. mdx. So the change in z we'll get from there is going to be, say, mx dx plus my dy.
Yep.
So we can calculate. All right, good. Keep going.
And then, so we would know mx.
What was that?
That would be respect to x.
Yeah, what do we call that? The rate of change with respect to x. Starts with p.
Partial derivative?
Yeah, that's the partial derivative with respect to x. Evaluated at
A.
AB.
B. Yeah. And then times change in x would be x minus a. And then plus my would be partial derivative of y at AB times y minus b. And that gives us dz.
Okay.
And then our initial point would be f of AB
Okay.
plus dz would give us 6.
Okay, good. So our z estimate, so we'll call it z estimate, is going to equal. So this, does everyone get that as the change, right? So there's going to be a change for our change in x. Your change in x is going to be x minus a. That's your dx. And if you take the rate of change times dx, you'll get the change in z because of the x change. And then the change in y will be y minus b. And if you multiply it by the rate of change in the y direction, you'll get the change in z due to the y change. And we can just add them together, right? Because there's no overlap there. They're in orthogonal directions to one another. So then our z estimate would be, did anyone get it from there? Megan, did you get it from there? How would I use that to get the z estimate for this new point? Okay, good. So it would be f of AB. So I'll write the dz first. So it's going to be the dz. I don't want to erase, but I can't go to the borders here. It's not happy. All right, so we'll try plus By the bottom. So then that's the change in z plus f of AB. Ah, I knew it. Okay. So that's review. It's just all symbolic now, right? It's just all symbolic. So this would be if you moved a little bit around, close to AB, if you moved a little bit away. This is using all the information we know about around AB to estimate the new z that you would get if you moved a little bit away from AB. Right? So the change, the total change from your x change and your y change plus the original z will give you the new z estimate. Okay, so we'll put that on hold for a second here. And let's look at a different question. Any questions about that? Can I erase? Okay, erase and restart my. Restart this one. Okay, so now I want to look at this. Here. What I'm showing here is a line that's tangent to the plane, the surface, sorry, tangent to the surface, and then in the x direction. So your next task is to write the equation of this line. Could you write the equation of based on, again, with a point AB, comma, f of AB, right? So that's our point of tangency is AB, f of AB. Same point as before. Can you write the equation of the tangent line that's parallel to the xz, parallel to the xz plane? Yeah. Can you do it? That's your task. So we got to remember about equations of lines in R3, right? So you first think, okay, how do I write the equation of a line in R3? What do I need? What do I need? And then how can the given information get me what I need? Okay, go. Okay, let's see what you came up with. So how about Sarah? Anything? Did you come up with anything about this? How about what do you need to write the equation of a line? What are we going to need to write the equation of a line in space? Don't remember, okay? Travis.
Well, for the director, for a line, you have a point and direction vector.
All right, so we need a point and direction vector. Either of those easy? Do we have either of those? So what's our point? Yeah, so we got a point on the line. Any point will do, but we only have one, right? We got that point of tangency. A, B, F, A, B. Okay, good. And so now we need the direction vector. So our direction vector is parallel or orthogonal to the line? Parallel, right? For direction for a line, it points in the direction of the line, right? Okay, so do we know anything about that? A vector parallel to that, we need to get that direction vector. Can we say anything?
There's no y component.
No y component, agree? Yeah, there's no change in y, right? So we can go 0 here. So all we got to do now is figure out how do we have an x and z component that show the direction of that line. So what do we have to help us with that? What's that? Yeah, so which derivative?
Would it be just the regular one?
In R3, what? So there's not just a derivative, right? We got lots of more to talk about than just derivative. Okay, is it a partial derivative? It's going to help us? Which one? X, right? The partial with respect to x is giving us the rate of change of the surface in the x direction. So that's going to be like the rate of change of our line, right? So we got the partial with respect to x we can use. How are we going to then choose our x and z components? So this using the partial so that we Show the direction of that line. Anyone come up with it? Jonas.
So for any change in x,
Right.
there's going to be a change in z that's going to be f of x ab times that number.
Good.
So if you just make x equal to 1 for our direction vector,
Yeah.
the z component would just be f of x ab.
Did you hear that? Right? So the change in z is always the partial derivative times whatever change in x you pick. So pick a change at x of 1, and then what's your corresponding change in z? Partial derivative with respect to x. Pretty slick, right? So now we want to write the equation of the line. What is the equation of the line then? Vector A. Vector AB. F of AB. Scalar T times, I don't have room, that. So that's our vector equation of the line. You start with a point, and then plus any scalar multiple of our direction vector gives us all the points on the line, right? Okay, so now we could pretty quickly write down, so based on the pattern here, this one, the red one. So what's our point for the red one?
Same point.
Same point. So now, in red here. So for the y direction line, meaning parallel to the what? Parallel to the YZ plane. Our point is same. And our direction vector is? Right, so this is easy now. X doesn't change, and then we change it, pick a Y change of 1, and then the Z would change by 1 times that, or just partial with respect to, or the partial with respect to Y times 1. Okay, so now those two lines form a plane, right? Find the equation of the plane that those are formed by those two lines. Go. Find the equation of the plane that is formed by those two lines. You didn't know you'd have so much fun in class today, right? This plane. So when I do the cross product, I get negative partial with respect to x, negative partial with respect to y, and 1. Did you get that?
Yep.
So that vector is normal to the plane. Okay, and the point we can use? Same point again. And so remember how to write, given a point and normal vector, how to write the equation? Here we go. So what am I going to write? Negative fx, and we know that's at AB, right? Times x minus a plus times 1 times z minus FAB equals 0. Yep, so our coefficients are the normal vector, and then we have all points on the plane, x, y, z, right? All points on the plane. And then our, whatever point we're using, the specific point, a, b, in this case, a, b, f, a, b, f of a, b. Questions on that? Okay, now I want you to solve this for z. Take this equation and solve it for z, and see what you get. Did you see it? Figure out? So Astrid, what'd you get? Did you change it around and solve for z? You weren't able to? You didn't do the algebra?
Yes.
Trinity, tell me.
I got b equals f of x, x minus a,
Okay.
f of y, y minus e, plus f of a.
So what are we saying? Z coordinates on the plane. That's what we're solving for. We solve for z coordinates on the plane. You notice anything? Yanni, what'd you notice? What'd you say?
So I know the FAB equals to the third of FAB
I'm not tracking with you. Actually, that's right. And I want to actually this time let's write, because it's a value f of x evaluated at AB, and f of y evaluated at room. Him.
It's the gradient of the thing plus f of a and b.
It's the grade. What's the gradient?
The gradient like f of x, that's when I say like f of y, if I'm going to get the gradient and then add it.
The gradient is the vector of the partial derivative. So the gradient is kind of like this vector.
Oh, sorry, like if you were to dot that with the unit vector and then add that.
Is it a unit vector? Yeah, so you're seeing the dot product. You're seeing kind of this gradient dot changes.
Yeah.
Okay. Any other observations? Yeah.
It's the same for our estimate as you did earlier.
So do you remember what our z estimate was earlier in class? Z estimate, if we make a little change, if we change that point to xy, what was our z estimate?
Same thing.
Exact same thing. So when we do this, so what's the conclusion, right? So the z. So if you move a little bit away from this point, and you find an estimate of your new z value based on what partial derivatives, what are you really doing? What's really happening there, Andrew?
Removing the line.
Right. So right around this point, the plane gives us the estimated z values. That the tangent plane is giving us the estimated z values based on partial derivatives, right? Because partial derivatives are based on constant rate of change, right? dz equals partial of x dx. That's linear. That's constant rate of change. Same with, also f of y dy. So if we're using partial derivatives to estimate changes, we're using a linear approximation. Well, so that's what the tangent plane is. So values of z on that tangent plane close to our point will be the estimates that we get. So we kind of did the same thing twice, right? We did the same thing twice, talking about the what would be the estimated z that you would get if you changed away from AB a little bit, and finding all z values on the tangent plane. It's one and the same. It's the same thing. Oh, come on, it's cooler than that. All right. So this is called the linear. So rather than z, we call it the linearization of the surface. so like usually often it's called capital L x y. So this is a new function, and it's the gray surface, right? It's the tangent plane, and it helps us. What it does for us is it gets us estimates of the z value, the function value, if we stay close enough to the point that we started at. Because if you move away, right? So what happens if you move too far away from point xy? Well, that plane, that surface starts deviating away from the plane. But close to that point, the plane and the surface are the plane is a good approximation of the surface. So this is called the linearization of the surface at AB. So it's equal to z estimate, and it's the equation of the tangent plane. They're one and the same. Estimates of z around that point and the tangent plane, that's one and the same, the linearization of the surface. Okay, so let's look at all right, and so there's the linearization is when you actually add the old z value and you're estimating new z values. The differential is just this part, right? The differential we've done many times. That's just the dz part. So the differential so that you'll have problems that talk about the linearization or find an approximation for the value of the function. Well, that's using the linearization. If you want you're trying to approximate the change, well, that's a matter of the differential, and that just goes back to just this part of it, right? So this much of it is the dz. Does that green show up good? Good, perfect. That's the dz only, and that's called the differential. The partial times the change in x plus the partial times the change in y. Okay, so let's look at an example. Any questions on this? So, dz differential. Can I erase? Any questions? All right, so here's this problem says. Maybe. A large block of ice is 4 feet by 4 feet by 1.5 feet tall. As it melts, the height decreases fast, twice as fast as each of the lateral square lengths. Use differentials to estimate the change in volume that occurs when the height decreases by 1 inch. So we know that differentials is black. dz equals partial respect to x dx plus partial respect to y dy. That's our differential. So how does this problem, how do we define our quantities in this problem? What is length? What is height? What is width? What is volume here? If our differential we know is partial x with respect to x plus partial y with respect to y. So what would our z be? What would our x be in this situation? So it says use differentials to estimate what? The change in volume that occurs when the height decreases by 1 inch. So how does volume fit into this? They want z in front. Should volume be z? So we're really saying dv, right? dv equals. And then what's our x and y here?
The height and then the side length of the squares.
Okay, good. So we could say the height, is what we could say the partial with respect to h, dh, And then, so that'd be height. So z is like volume, I'm saying, and y is like height. And then x is like, say, s for side length, so f sub s ds. So now how are we going to get this dv equation? We got the form of it, we got the structure of it, but how am I going to get dv actually equals something that I can solve for? Where's that going to come from? So this f of s is really what? Volume s, right? When I say f, now we're talking about, let's talk about the volume function. So that's the partial derivative. So that's the partial derivative of volume with respect to side length and partial derivative of volume with respect to h. That's what I mean by those. So where are we going to get those? How are we going to get those?
So volume equals side length squared times
Right.
height.
This is a block with this constant square and the height. So then tell me what dv equals. dv equals partial of volume with respect to side length. 2hs or 2sh times the change in s plus partial with respect to height, s squared dh. What's s? 4. What's h? 1.5. What's ds? Okay, this one is, yeah, right, so we know what s is. So dh, it says the height decreases by 1 inch. -1. And that's changing twice as fast as the sides. This is -1/2 then? But these are, we need feet, right? We need feet. Home free. Now we can get, so that will calculate what? The change in volume based on those changes in side length and height and the current side length and height.